Hi and welcome to my presentation. This presentation explores a particular mathematics misconception and provides 2 resources I recommend to intervene, resolve or overcome the misconception. The misconception in focus in this presentation is common in young students learning about fractions. It is the misconception which occurs particularly when comparing fractions that the larger the denominator, the larger the fraction. For example, when asked which of these fractions is greater, 1/10 versus 1/2, they select 1/10. Their understanding is that high numbers are always greater than low numbers and sometimes find it difficult to accept the changes to this rule which occur when learning fractions. The following resources, when used appropriately, can assist with preventing or correcting this misconception from evolving. This misconception is commonly formed in Year 3 as the curriculum requires students to model and represent unit fractions and their multiples, including 1/2, 1/4, 1/3 and 1/5. The first resource we will be looking at is fraction blocks. Fraction blocks are physical manipulatives which allow students to physically experience the size difference between different fractions. Students can see that one whole, when split into different fractions, becomes different sized pieces depending on the fraction, in particular the denominator. Students can physically see that the larger the denominator in the fraction, the more pieces the whole is split into, and therefore the smaller the pieces become. Students' developmental stages often dictate the style of pedagogy which will be the most beneficial to building their mathematics understandings. In Year 3, students are 8 to 9 years old. According to Piaget, students of this age are in the concrete operational stage, suggesting that children are now beginning to think logically and systematically in concrete situations. Therefore, their ability to comprehend abstract concepts is still developing, and they rely on concrete experiences, such as learning with manipulatives like the fraction box, in order to develop understanding of the concepts of fractions. Beginning with concrete materials assists children in moving through Bruner's concrete representational abstract framework, or the CRA framework. This suggests that students need to have concrete experiences with mathematical concepts before they can comprehend representational concepts, like understanding a fraction worksheet made up of pictures. And only then can they move into abstract understanding, where they can understand fractions written in their numerical form without assisting pictures or manipulatives. Working at the developmentally appropriate level and providing students with manipulatives has a very positive effect on student engagement. Working with concrete manipulatives allows students to investigate and explore at their own pace. And maths anxieties are subdued as students can physically see the concept before them. Students at a young age are often kinesthetically and visually driven, and so the fraction blocks appeal to the tactile nature of the students, much like toys do. This positive engagement makes a huge difference in academic outcomes. There are infinite ways to use fraction blocks to the advantage of your students. Some of these strategies include involving them with the initial teaching of fractions and their comparative sizes, using them for checking answers, and using them as exit tickets. When initially teaching students about fractions, the blocks can be used to show their comparative size early on, even in Year 2, when students are introduced to quarters and eighths. When first learning simple fractions, comparing the relative size of these fractions at the beginning will help to prevent a wide range of misconceptions from forming and assist with equivalent fractions later on. Fraction blocks make it easy and simple to do this. The blocks can also be stacked with different types of fractions to represent how the same value can be created with mismatching fractions. For example, stacking 1/2, 2/8 and 1/4 on top of each other will create a stack the same height as the whole. Using these blocks when discussing fractions and their sizes helps students contextualize and visualize the mathematic concept and construct a better understanding. Another strategy for use is using the blocks to check answers. For example, as a class, 2 fractions could be presented in their numerical value on the board, and students are asked to think about which is bigger. The teacher can then present students with the corresponding fraction blocks to physically show which is greater, and can relate back to the concept that the denominator denotes how many pieces the whole is cut into, and therefore the unit fraction becomes smaller with a larger denominator. This same strategy can also be used to compare non-unit fractions and prevent the misconception larger denominators always mean smaller values from evolving. For example, when asked which is greater, 3/5 or 2/4, they reply 2/4 because it has a smaller denominator. Using the fraction blocks to compare non-unit fractions can help prevent this from occurring. Finally, a similar strategy can be applied in which the fraction blocks are used as an exit ticket. Each student is asked to pick the larger of the two fractions and are presented with the corresponding fraction blocks after their answer. This allows the teacher to assess each child's understanding of comparative fractions and allows the student individual time with the teacher in which the physical representation of the question is provided to them and, if they answer incorrectly, allows them to see why they were incorrect. This exit ticket reinforces the idea of relative fraction sizes and therefore addresses the misconception that the larger denominator fraction is always the larger value. The ICT resource I have chosen is an online game from Soft Schools called simply Ordering Fractions. In the game, students select whether they want to order fractions from least to greatest or from greatest to least, and then are provided with 4 fractions, both numerically and pictorially represented, which they then must drag and drop to place in their correct order. There are 5 rounds, and the total time taken to complete is measured. The game uses both unit and non-unit fractions. Children at this level are theorised by Piaget to be in the concrete operational stage, as previously discussed, and have the ability to use logic in concrete situations. Technically, the laws of this theory would mean that students would be unable to complete the ordering game as there is no concrete manipulative involved. However, if this task is used as a consolidation exercise, students' prior experience with concrete manipulatives should directly translate into the pictorial representations of the fractions within the game, which are then paired with the numerical or abstract representation. This progression is moving through the CRA framework. Students should be able to rely on the pictorial representation to use their problem-solving skills and correctly arrange the fractions. Erikson's theory of personality suggests that students of this age are also developing the sense of independence and self-confidence. The nature of online games, such as this one, allows students to work independently and at their own pace, and must rely on themselves to utilise critical thinking and problem-solving skills to correctly finish the game. Our students are children of the technology era. They are constantly involved with devices and ICTs from an exceedingly young age, and often many of their interests revolve around a screen. Because of this, the involvement of an online game has a very positive effect on student engagement. The game format of the resource also adds an element of fun and enjoyment to the subject, providing relief from the sometimes dry nature of mathematics education. Another highly engaging element of the game is its timer feature. Students with a competitive nature can time themselves and challenge others to beat the time or make a new personal best. This speed element of the game helps students practice and improve their mathematical fluency as well as their understanding, reasoning and problem-solving skills. This game would be used most effectively as a consolidation exercise. It would not be helpful for students who are first learning the concept of fraction comparison and would hinder their confidence in learning. Instead, it should be used after the initial teaching of the concept. The game can be played individually, the most popular strategy for its use. Students could be asked to complete the game 3 times and record their time after each round. This strategy ensures students are actively thinking about their performance and are actively working to improve. The game, when used in this way, helps to address the misconception by familiarising students with both the pictorial and numerical representation of fractions in relation to one another. The high frequency and repetition of the challenge allows students to access and respond to the concept over and over with instant feedback in the accuracy of their attempts. This addresses the misconception by forcing students to visualise the physical representation of the fractions in relation to one another and discover that the denominator is not the deciding factor in which is greater. Another strategy for use of the game is using it as a class. The educator picks a volunteer to complete the game in front of the class and then asks them to explain their strategy. The teacher could then do a live version of the game without the pictorial representations, meaning the teacher would draw 4 empty boxes on the board and underneath write 4 fractions in their numerical form. Students could then order them from least to greatest on their individual whiteboards before going through the answers as a class. asking students to explain their reasoning and strategies as they go. This strategy addresses the misconception by scaffolding progress even further through the CRA framework, helping students to step up into understanding the relative size of fractions without needing pictorial representations, or learning strategies in which they draw the fraction if they're unsure. To be able to do this, students must understand that the fraction is a whole divided by the denominator, and therefore understand that unit fractions get smaller as the denominator gets larger. Fractions are hard. Without the proper scaffolding, concrete, pictorial, and abstract experiences, students can develop gaps in their understanding which can affect their mathematical understanding throughout their lives. Resources such as the fraction blocks and the online ordering game help students to progressively learn relative fraction size and consequently prevent the development of the misconception formed from experiences with natural numbers that the larger denominator is the larger value. The skillful and developmentally appropriate use of these resources will determine their effectiveness, and I hope my presentation today has given you some ideas on how to effectively utilize these resources in your classroom. Thank you for listening. Bye!